Okay, so the context of the Vicky Climate Initiative goes back to the Siaki period, or the Siaki initiative, and of course it had to do with the Millennium Drought. And if we just look at the right-hand plot there, that's the time series of rainfall in averaged over Victoria during the cool season, which matters to our water resources in Victoria, so April through October from 1900 to 2016. And the outstanding feature on that plot is this period of 9 years in a row, the so-called Millennium Drought, where we didn't have a single above average year. That was broken spectacularly in 2010 by a La Nina event, but then we went back to another 5 years in a row of dry conditions. And again, this was actually after the end of the Vicky research period. We had another above average year in 2016 due to the so-called negative Indian Ocean dipole event. So we've sort of seen this about a 15% decline in rainfall, but we had this very extreme drought condition at the start of the 21st century. On the temperature side, we've seen a steady increase in temperatures over the last 100 years, and temperatures have increased in Victoria by about 1 degree, reflective of global warming that we've experienced in Australia-wide and around the world. So the key message is that we're in a drying climate, but still a climate that exhibits large variability. Just as an update, I know people are interested in what's been going on this year. We're back to dry conditions this year. This is just the early winter rainfall deciles for 2017. And there's areas in Victoria, sort of central Victoria, driest on record, and large areas in the west and in the southern parts of South Australia that are extremely dry. Okay, so to put this in a broader context, we can look at this last 30-year period from an Australian-wide view. And if we look just on the left, that's the cool season, that's the cool season rainfall decile for this period, 1986 to 2015. And I flagged that was the data we had available through the end of the Vicky research project. And so this period of, these dry conditions we've experienced in Victoria have not happened in isolation. It's been dry in southwest WA, been dry across the southern parts of South Australia, and dry up the east coast. So this is important, that we're not just seeing drying in southeastern Australia in isolation. It's reflective of large-scale drying across the southern part of the continent. One of the most intriguing things about our climate is if we look in the other half of the year, in the warm season, the continent's getting wetter. It's remarkable, right? The contrast is remarkable. If you look carefully in Victoria, it's really only the northern part of Victoria that's been getting wetter. The southern part is sort of stayed neutral, but it hasn't had much change. But the contrast is remarkable. Okay, and so in a broad sense, then, the climate aspect of the Vicky research program was trying to address, why has winter and the cool season dried, but the summer season's gotten wetter? Can we expect that trend to continue in the future? And then as Grace pointed out, we also had a seasonal prediction aspect of this project. And essentially we were trying to address the question as, has our seasonal prediction capability increased so that we can better anticipate and manage these year-to-year variations, especially the extreme years. And we want to be able to manage those years because, we're having that variability on top of these ongoing trends. Okay, now this was supposed to be a simple diagram. I'll sort of talk you to it. The science we brought, the climate science we brought to the Victorian Climate Initiative was to better understand how weather systems which are bringing rainfall to Victoria are interacting and being influenced by the large-scale climate. And we sort of tried to include schematically on here all of the key features that matter and have changed associated with climate in the southeast. And so, we've indicated that one key source of rainfall is frontal weather systems that are traversing from west to east in the mid-latitude westerly jet stream, primarily affecting rainfall across the south of the state. Occasionally we get east coast lows that develop and bring heavy rainfall to Gippsland. We sometimes get, the frontal systems connect with an upper level trough and can bring moisture in from the north, primarily affecting to the north of the divide. A key feature that matters, and we'll highlight in the rest of this talk, is this ridge of high pressure, which we call the subtropical ridge. And it's, in wintertime, it sits pretty much over the central, its axis sits across the central part of the country. In summer, it shifts south. So in winter, when it shifts north, we can get more penetration of weather systems across the south of the country, bringing rainfall. In summer, it shifts south, and if it shifts far enough south, we bring tropical conditions into the state. Okay, so what are some of the research areas we focused on? Well, one was the position and intensity of the mid-latitude jet, which is the source of these frontal systems, which are bringing rain to especially the south part of the state. And the position of this jet tends to wobble north and south, and its variation, we call it the southern annular mode, or SAM. And it's in its low phase, when the jet is closer to the equator, you tend to see more frontal activity and more rainfall in the winter. And in its high phase, it moves away from the continent, and we tend to get drier conditions. Okay, another key aspect, another key driver of the circulation then is also what's going on in the tropics. So it's well known to many people that a key driver of our wet and dry years is El Nino and La Nina. The Vicky research highlighted that equally important to El Nino and La Nina is what's going on in the Indian Ocean. We refer to that as the Indian Ocean dipole, and it's effectively the cousin of El Nino in the Indian Ocean. And a lot of the influence that we experience due to El Nino and La Nina in the southeast part of the country is actually coming through the covariation of El Nino and La Nina in the Pacific with the Indian Ocean dipole, which then drives a response over southeast. Now, on top of that, there's slower variations in the climate, which are decadal variations in the climate, primarily in the tropics. And they have time scales, say, from 5 years to 20 years, and it's primarily natural variability. And the Vicky research highlighted how that decadal variation is actually interacting with El Nino and the Indian Ocean dipole and then influencing how they are affecting Victorian climate. And then furthermore, on top of all that, we have global warming. And global warming affects the climate in multiple ways, but two key things it's doing for us is it's affecting where the subtropical ridge is. And so if it's pushing the ridge further south in the winter, it could be acting to dry the climate. It's also influencing the behavior of El Nino and the Indian Ocean dipole and affecting how those phenomena affect Victorian climate. So it's a rather complicated picture, but that's the key research areas we focused on. For the rest of the talk, the primary thing we want to talk about is what's driving the variability in the subtropical ridge, and associated with that, how is the westerly jet at higher latitudes behaving? A convenient way to understand and summarize what's going on with the subtropical ridge is to look at the climate in an average sense in the east-west direction. And when you do that, you reveal the so-called mean meridional circulation. So if you average the climate around latitude circles, you see the circulation. And so in the schematic view here's the South Pole, here's the equator, and a beautiful representation of Australia right here. And we sit here roughly at Victoria right here. When you look at the vertical axis then is from the surface up through the top of the troposphere and lower stratosphere. When you look at the circulation in this way, we reveal 3 overturning cells. A well-known cell in the tropics is referred to as the Hadley circulation, where there's upward motion being driven by the warm ocean temperatures in the tropics and deep tropical convection. The outflow of that cell then flows poleward and feeds into the subtropical jet, and it converges and sinks. And where that maximum sinking motion is occurring is the position of the subtropical jet. And you can see, subtropical ridge. And you can see that's roughly in the winter, that's over the central part of the country, but in the summer it's more even to the south of Victoria. On the poleward side of this Hadley circulation, we have the other circulation cell, which contains the westerly jet. And associated with that westerly jet then is the mid-latitude storm track. And it's those storms then that are bringing rainfall across the south of the country. And so a key thing to realize is that Victoria sits right at the southern edge of this descending branch of the Hadley circulation, and at the northern edge of this return cell, this storm track. All right, so it's easy to understand then that Victorian climate is susceptible to variations both into this Hadley circulation cell and into variations of the higher latitude cell, which contains the westerly jet. And in a general way, or general sense, you might imagine if this Hadley cell expands in the summertime, that will bring more tropical conditions to, at least to the northern part of the state. But as the cell expands in the wintertime, it's going to act to push the storm track further away from the continent. So expansion of the tropics, could be good news in the summer, but bad news in the winter. That's sort of the take-home message of that, thinking about it in a simplistic way. Okay, so with that context, why has it gotten drier in Victoria in the last 30 years? And it's a very simple message from this. It's because that subtropical ridge has gotten stronger. And a way to visualize that, this is actually, a typical weather forecast map you would see on TV. This was produced 3 or 4 days ago at the Bureau. And so you see, this is the surface pressure they've displayed here. You see these 3 cells of high pressure, and I've sort of connected the highest pressure center together. We refer to that as the subtropical ridge. So for that day last week, that's where the subtropical ridge was. You can see for that particular day, there was a frontal system approaching WA, and the green is the rainfall, the expected rainfall with that system. There was also a weak cutoff low system on the East Coast, bringing a little bit of rainfall up the East Coast. But you can imagine then the penetration of these weather systems and East Coast lows towards the continent is really going to depend on how strong the pressure is in the subtropical ridge. And if you just simply average the pressure in that box for the last, whatever that is, 40 years, and this is just for the cool season, we've seen the pressure across the south of Australia essentially go up 3 millibars, so 3 hectopascals in the last 40 years. All right, there's a lot of variability associated with El Nino and La Nina and so forth, but pressures have been steadily rising. If you look at that in a plan view, so we can compute that pressure trend at every grid point over the hemisphere, and this is the plot that's actually in the synthesis report. You can see it's not just happened in isolation. Pressures have gone up everywhere at the sort of the edge of the subtropics across the southern hemisphere. The bad news for Australia is we've suffered the greatest increase. So the greatest increase in surface pressure in the last 30 or 40 years has actually been to the south of Australia, but it's part of this overall coherent increase in pressures around the hemisphere. So now we can conveniently contrast what's happened in winter and summer. The plot up there on the right is the plot I just showed you for winter, and the plot below that is a sort of a hastily made version of rainfall averaged across all of the south of Australia. So associated with that pressure rise in the cool season, the winter season, rainfall across all of southern Australia has steadily declined. Contrast that with summer, we see the same general pattern of pressure increases in the subtropics to mid-latitudes, but it's happened to the south of Australia, right? And this reflects partly the seasonal cycle, that the subtropical ridge is normally in the middle of Australia in winter, and it's the south of Australia in summer. And so we've seen, the same sort of pattern, but it's shifted south. But because it's happened to the south, it's made essentially Australia more tropical. And if you look at the rainfall averaged across the south of Australia for that same period for the last 30 years, it's steadily increased. Okay, so the summary is, and the winter rainfall has decreased because, we've strengthened the subtropical ridge, effectively deflecting southward the weather system that bring us rain. Summer rainfalls increased because the tropics have expanded and with the southward shifted ridge. But importantly, there's a subtlety here, another subtlety. If you look at the pressure pattern in the lower latitudes in the tropics, you actually see something that's more asymmetric than what we see in the higher latitudes. In fact, so we've seen pressures go up in the equatorial eastern Pacific and pressures go down in the tropical Indian Ocean. And that pressure pattern is reminiscent or similar to what we get during La Nina. We refer to this as the high phase of the Southern Oscillation. Right? And so on top of this southward shift of the high pressure in the summer, which is making Australia more tropical, we've also got this extra push coming from this La Nina-like pressure trend in the tropics. Okay, so where did that come from? And the answer of where that came from is because it's reflective of how ocean temperatures have changed in the last 30 years. And if you look at the pattern there on the left, that's the change in ocean temperatures that we've experienced from 1979 up through 2015. And it's, there's Africa and Australia and South America. And so what we've seen is temperatures have gone up everywhere in the Indian Ocean and Western Pacific, but they've lagged behind in the Eastern Pacific. And so that's a very much La Nina-like pattern that we've experienced. But you could ask, how much of that's due to global warming and how much of that's due to natural variability in the climate system? And one way to answer that question is you can turn to the climate models that we use to do our climate change projection work and use those models to simulate the climate for 1979 to 2015. And we've averaged over about 30 model simulations here. And so these models are driven the models are just forced with the increased greenhouse gases that we've experienced over that period. And if you compute the trend from those models in ocean temperatures for that period, you see something quite different. You see much more uniform warming, and in fact you see enhanced warming in the Eastern Pacific. And so we interpret the difference between these two patterns as the role that natural decadal variability has played. And so what we've seen in the last 30 years then is some sort of combination of this natural decadal variability, which has been this La Nina-like pattern, on top of some global warming, which maybe accounts for the warming that's happened in the Indian Ocean. Importantly then, that La Nina-like pattern that we've experienced for the last 30 years, which has just been, it's just been a natural variation in the climate, it's acted to expand the tropics in the Australian sector, making summer wetter in Australia. But importantly, as we move into the 21st century, we sort of expect more warming pattern like this to emerge. And that's not going to be a pattern that's favored this expansion in the Australian sector. Okay, so returning back to trying to diagnose, the behavior of the extent of the tropics and the position of the subtropical ridge, we've quantified the trend in the poleward extent of the tropics for the period, for the recent period 79 to 2015. And what's displayed here is the change in latitude of the southward change in latitude of the extent of the tropics, over the poleward edge of the tropics. And there's two bars here. There's the green bar is if we look at that over in the entire hemisphere, and the blue bars are if we just make that measurement in the Australian sector. And we've computed that trend for every month of the year in a 3-month running mean. And so the summer season's on the left here, winter's in the middle, and back to spring and summer here. And there's two key messages from this plot, is that most of the expansions happen during summer. There's the edge of the tropics, the edge of the subtropical ridge has moved about 1/2 degree poleward in 30 years, primarily in the summer, much less so in the winter. The other message is the expansion has happened at about double the rate over the hemisphere in the Australian sector. So the ridge has almost moved a degree in summer in the Australian sector, and maybe more, 1/2 degree during winter. Okay. This measure actually focused on the position of the subtropical ridge. We could have equally done the same thing measuring the position of the westerly jet. It turns out the shift in the westerly jet is about double the shift in the edge of the subtropical ridge. So the westerly jet has moved more than a degree southward, while the subtropical ridge has moved less than a degree. Okay, so the summary is then that this expansion of the tropics has acted to increase subtropical rainfall during the Australian summer. It's contributed to the winter drying, but we think equally important to the winter drying has been the intensification of the overturning circulation, not just the fact that it's shifted. Climate model experiments and other work done outside of the Vicky program have attributed this expansion, and especially the seasonality of this expansion. And the conclusions are that most of the expansion that we've seen in the last 30 years is due to this La Nina-like pattern of warming that we've seen, of decadal variability in the tropical oceans, together with Antarctic ozone depletion. So you're probably well aware that ozone hole was discovered, in about 1980, and it's primarily a summertime phenomenon. And that depletion of ozone then acts to shift the westerly jet towards the pole and expand the tropics. So most of the seasonality, most of the expansion that's happened in the summer, we think reflects the fact that we've had this La Nina-like pattern, decadal variability in the tropics, on top of ozone depletion. The climate model suggests there is a role for greenhouse gas forcing for what we've observed, but it's a more minor player than what's actually than these other two components. What's going to happen next? So we're looking at projections now for the 21st century, and we again return to looking at the models used for the IPCC assessments, the CMIP-5 models, and this is the RCP 8.5 scenarios, looking at the trend in the position of the westerly jet for the period, or the change in the position of the westerly jet for the period 1979 to the end of the 21st century. Okay, and the red curve then is the multi-model mean. It's about 30 model mean of how that jet's going to change over the next 100 years. And the unit here is effectively the degrees latitude southward shift of the jet. And so what this is telling us is that pretty much independent of time of year, we expect over the next 100 years for the westerly jet to shift effectively another 2 degrees south. And of course, the implication for that is, and that's primarily in response to the greenhouse gas forcing, the implication of that is that's going to act to shift the storm track further away from Victoria, and wintertime drying then would be promoted by this ongoing trend of shifting the jet away from Australia. One key thing from this plot is, in fact, there's actually less confidence in how much shift we're going to get in the summer, and that's completely the opposite of what we've experienced in the last 30 years. What we've seen in the last 30 years is most of the shift has happened during summer. And the reason that we don't see as much shift during summer is because we project that the ozone hole will recover. They keep moving back. People's estimates of when the ozone hole is going to recover keep shifting further out, but by mid-century it's supposed to recover. And so this accelerated expansion during summer is slowed, and we actually, the shading here is indicative of some range of uncertainty across the model. So there's less certainty about the expansion that will happen in summer in the future. Now, importantly, this is a really broad scale view of how the circulation is going to change, and to really understand what's going to happen and what it means for Victoria, you need to use other approaches. For instance, downscaling what you get from the climate models down to the scale of the state of Victoria, both to quantify rainfall and streamfall impacts. And in a minute, Francis is going to tell you about that work that was done in Vicky. Okay, that was it on the climate projection side. There's one slide here on what the work we did some of the work we did in seasonal prediction. During the course of the Vicky project, the Bureau of Meteorology started to upgrade its seasonal prediction system, which used to be called the Poema model, or was the Poema model, and we're upgrading that system to this new system called Access Seasonal Prediction System, so Access S. Access S has much higher resolution and it's a much newer model than the Poema model. And it's going to form the basis for the new seasonal prediction service from the Bureau, and the date keeps getting pushed out, but currently that system will switch over and be operational in February 2018. So one thing we did in the Vicky program was to try to assess what sort of capability will that system have, especially of relevance to Victoria. And one thing we, of course, wanted to assess is how well can we predict El Nino with that system, and how well, and how do we compare with what we were able to do with Poema. And a really pleasing outcome of the new forecast system is our ability to predict El Nino from initial start times in the autumn. And this summarizes that improvement. So we reran the system from 1990 to 2012, starting on the 1st of May every year. And we've scored these forecasts using some index of El Nino. We call this the Nino 3-4 index, which is just simply the ocean temperatures averaged in the equatorial Pacific, which is a good indicator of El Nino. And the forecast performance is based just on a correlation coefficient. And so 1 is a perfect forecast. And we look at the forecast then for that, how well we do with the forecast from May out through September. And the red curve is the new model. The blue curve is the old model. And this is really outstanding improvement. And this is an important time because this autumn time gets referred to as the autumn predictability barrier because it's the time of year where El Nino starts to develop and could go either way. And it's the time of year that's most challenging to predict. And we've really made, the new model really is going to offer improved capability to make predictions from the autumn. That's especially important for water resource management because this is at the start, prior to the start of the filling season. And if we actually look at what it means for predicting rainfall in Victoria, and this particular view, we're just looking at how well we can predict above or below median rainfall. So we run the system as an ensemble system, and we make a probabilistic forecast saying, the chances are increased or decreased to be above or below median. And we look at for the July through September period from the forecast started from the 1st of May. And we score those forecasts just as a percentage correct. And so anything better than 50% presumably is better than chance. And we've just shaded it where it's better than 55%. And you can see in the new model, broadly, maybe not such good news for Gippsland, but to the north of the dividing range, we have much improved skill from the new model from what we had in Poema. And in fact, the grid size there is indicative of the resolution. And you can see one of the problems in Poema is, we essentially didn't really resolve Victoria very well. And so this is really a very promising result. So let me just wrap up here then. Just a summary of the key messages from the climate side. So in the past 30 years, the tropics have been expanding, the subtropical ridge has been strengthening, and the storm track has shifted poleward. This is acting in a broad scale sense to promote winter drying, but summer's getting wetter. A certain amount of that tropical expansion is certainly linked to global warming, but at least in the recent 30 years or so, most of that expansion has been driven by this La Nina-like natural decadal variation of tropical ocean temperatures, and at least in the summer by Antarctic ozone depletion. The projections are that as we go into the 21st century, global warming is going to continue to act to shift the storm track forward. We think warm season rainfall won't increase at the same rate that we've seen recently, mostly because ozone will recover. And so it's not clear at all that we would have much faith that that we'll have reliable increases in warm season rainfall, and especially increases that would be enough to offset cool season declines. I didn't have time to talk about this, but this second to last dot point is very important. Victorian climate will continue to exhibit large year-to-year variations under the influence of El Nino and La Nina and the Indian Ocean dipole, as well as decadal variability. So even though we expect, our climate's going to become drier and warmer, we still expect large year-to-year variations. El Nino and the Indian Ocean dipole are not going to go away in a future climate. But equally important, and we've showed this in our research in Vicky, is that El Nino and the Indian Ocean dipole can interact with this forced warming trend, and it can lead to amplified impacts on Victorian rainfall. And this is a very good example was what happened in 2010. We received a lot more rainfall in that La Nina event in 2010 than we may have expected because of the ongoing warming trend in the Indian Ocean. We're still working on a project right now to understand what happened in 2016, but indications are 2016 something similar happened, that this so-called negative dipole event developed on the back of this background warming that has been going on in the Indian Ocean. Okay, and I guess a final plug for our seasonal prediction capability. As we move into this new access system, it looks like it should be a potential useful tool for managing seasonal variations of water resources, and I hope we'll come back and advertise that when we become operational, hopefully in February.